Hello guys, welcome to our next video in the playlist Google Earth Engine for the land cover applications. So in today's video, we are gonna see how we can detect the landslide occurrences in the region of Kodagu. So the major landslide has occurred in the Kodagu district of Karnataka in the southern India in the month of August, between August 10 and to the August 10 and August 17 in the year 2018. So we're gonna see how we can detect that using the satellite images. So we will have the two satellite images. One is before the occurrence of the disaster, and one is after the occurrence of the disaster. So we'll calculate the spectral distance in terms of the spectral angle mapper as well as the spectral squared Euclidean distance. So in both of it, we'll interpret how the reflectances of the spectrum has changed for the landslide region before and after occurrence of the disaster. So this is the area which I have selected where the landslide has occurred. So it's a little place in the region of Madkeri in the Kodagu district. So first of all, I'm going to create my region of interest with the help of a point. So let's pick a point and rename it as region of interest. And now we should have two images created, one for the before occurrence of landslide and one after the occurrence of landslide. So now we have to import a region a Sentinel-2 dataset. So remember, we are using in this case the Sentinel level 1C, not the level 2A, because the date range of the level 2A starts after 2018. So we are using the level 1C dataset here. So let's take the import and rename it as S2. So now I'm creating one more variable which is called as pre-image 1 because we need to multiply with the scalar with the scale value of 0.001 for all the satellite images. So we will have two pre-images, pre-image 1 and pre-image 2, and after that we'll write a function. We'll map it over the pre-image image collection so that our scale values will be multiplied. So you will understand once you see this video fully. So now we have our pre-image 1, and we have our Sentinel-2 data, and we are filtering it to bounds using the function filter bounds to the region of interest, and we are also filtering it to date. So we can take any date which is prior to the occurrence of 15th August or 10th August. So I'm taking 2018 January month because we'll have the less cloud cover. So the getting the cloud free images for the rainy season is very much difficult. In order to calculate the spectral distance, we need optical satellite images. So I have the January image data set now, and I have to filter it down to cloudy pixel percentage also. So I'm using e.filter function dot less than boolean functions, and I need to copy the cloudy pixel percentage from the metadata. So we need to go to our image properties in order to select the cloudy pixel percentage. Just copy the property and give it less than 1%. So let's see if we have any kind of images for the less than 1 cover percentage. So you just select pre-image and paste it in here. Click on the run. We have one element in here, so we just increase it to 5%. Yeah, we have three elements, that's enough. So now we are going to create one more variable called before image. So now for the pre-images which we have selected, which we have filtered, we have to map a function in order to multiply the scalar value. So I'm creating a function which takes input as an image, and it will return an image in return, but the values will be multiplied by 0.0001. So I need a median composite of it. So you use dot median function. That's it. Our before image is ready. We just add it to the map in order to see how does it look. So do the minimum value to be 0 and maximum value to be 0.3 after applying the scale, and the bands will be 4, 3 and 2. We are using the true color composite, and you can also rename the layer as before landslide. Okay, so after that you can also select the bands here. So I'm selecting only the bands which are starting with the B dot star. It means I don't need any other quality quality mask pixels like QA pixels. QA bands are all not needed, so I'm just selecting the B1, B2, B3 bands like that. So just click on the run now. Our layer is loading before landslide. So while it loads, you just select all of this code, and you can just paste it in here. So the cloud cover is more, so let's reduce the cloud cover to 3%. Still it's more. Yeah. So or else we can also change the date range if you want. So this much is okay. Now we'll change our pre-image to for the after images. So I'm just renaming it as, we are just manipulating our before image for the date. So it's August month after 15th. So you can take up to December because the recovery will be slow for the landslides. So up to December 30 I'm taking, and you'll just have the after image here, and this should be pre-image too, and here also you should add after image, and this should be written as after landslide. So give it a run. Let's see the differences from the satellite view for both the images. So yeah, now you can clearly see our two layers after landslide and before landslide have loaded. So if you want, you can expand it. So here you will clearly see the landslided areas. So since the cloud cover is more, let's take our before image a much prior date to 2017, 12/30, 12/1. Let's see. Yeah, now it looks good. So layers are loading. So if you can just see the prior image and the after image, clearly the landslide has affected our Kodagu region. So where the landslides has occurred, their spectral values will be different. So if you can just check on it. So here you will see on this region, the landslide has occurred. You will see the spectral differences over the region. So here you will see the before landslide values have more reflectance values. So there is a differences in both of them, before and after. So we need to calculate the spectral differences in terms of spectral distance and spectral angle, and we will add it to the map in order to visualize them better. So where there is a higher spectral differences or where more spectral distance is there, that area indicates where the landslide has occurred. So in order to calculate the spectral distance, we have a function called spectral distance in here, a built-in function. So it has the arguments image1 and image2, and it should also give the metric. So it will calculate in terms of spectral angle mapper, spectral information divergence, as well as the squared Euclidean distance, or EMD. So the most commonly used ones are spectral angle mapper in terms of the spectral angle, as well as the spectral not spectral, it's a squared Euclidean distance. So we'll see both of them in this video. So you just create a new variable called angle, which is a spectral angle. So we have our after image, for which we need to calculate the spectral distance, and we need to give the image to, that is our before image, and the metric will be in terms of uh, spectral squared Euclidean distance, not squared Euclidean distance, it's a spectral angle mapper, SAM. So our angle, spectral angle is calculated now in just one line. So I am adding it to the map in order to see how does it look. So spectral angle is written in the angle variable. So you can give the visualization parameters if you want. So minimum will be, let's say, 0, and maximum will be 1, and let's say uh, palette. So I'll choose white for the low angle differences, and red for the high angle distances, and you can rename it as spectral angle in here. So just give it a run now. So you can stretch this to 100%. So our value range is from 0.00 to 0.4. So you can have the palette. Just give it a run now. So while it loads, we'll also calculate the distance. So if you want, you can rename this as angle, and another will be distance. So here you will see our spectral angle is calculated. So where there are the landslides, there is high spectral angle can be seen. So where the landslides has occurred, you can see the regions in the red color. So those are the ones where the spectral distance is more. So we'll calculate in the other units also in terms of the squared Euclidean distance. So we are creating one more variable called distance. So for the after image, we are calculating the spectral distance with the use of the function spectral distance, and we are adding our before image to it, and it should have the unit or the metric in terms of SAM, that is spectral angle mapper. We have already calculated SED, squared Euclidean distance. So now we can add this to our map.add layer, uh, distance, and visualization parameters will be minimum 0 and maximum 0.3, and we should also give the palette. Let's say white for non-change colors, and blue for the higher spectral values, higher spectral distance values, and you can rename this layer as spectral distance. Give it a run. So I have spelling mistake here. Distance. So we have 4 layers. One is the before landslide image, after landslide image, and the spectral angle image, and the spectral distance image. So we'll see the differences in all of them. So in order to have a clear better visualization, let's stretch the range to 100%. So it's nearby only. So that's okay. So if you can compare the spectral distance with the satellite imagery, you will see the regions where the landslide has occurred have the higher spectral distance value. Similar to that, the spectral angle is also more where the landslide has occurred. So if you want some more information, you can click on the inspector column on the landslided region. So here you'll see our before band reflectances, after band reflectances, and the spectral angle and the spectral distance. So in the landslided area, the spectral angle is nearly 0.46 and 0.18. So if you can click on the non landslide region, there you will get a lower values for the spectral distance as well as the spectral angle. So here it is nearly 0.00. So I hope you have understood how to detect a landslide region and how we can compare the before and the after images for the landslides. So you can do it for any region if you have the cloud free uh, satellite images for your region for the date which is concerned. So I hope you have enjoyed the video, and if you have any kind of queries and doubts, you can always post it in the comment section. Thank you for watching. And we'll also share the script with the generated link in the description box, so you can always access it. Thank you for watching.